Okay. Our next speaker is Jeronimo Martinez. He's going to tell us about flat band localization and interaction-induced delocalization of photons.
Right. Hi everyone, my name is Jeronimo Martinez. Thank you so much for the organizers for letting me talk. So my name is Jeronimo. I am a grad student in the House Lab at Princeton University, and I'll be talking about this paper that we put on arXiv a few months ago looking at flat band physics and interactions on superconducting circuits. Okay, so first, a brief motivation for this. We're interested in looking at flat band physics. And what is interesting about flat band physics? So right now, that's a very active area of research in a lot of fields in physics. So one example of this is with magic angle twisted bilayer graphene, where if you look at the allowed energy levels of the electrons, you see one energy band here with respect to the lattice crystal momentum that is flat. And this is understood to give rise to a lot of strongly correlated physics that's seen with bilayer graphene, such as superconductivity. Another example is on Hall effect and Landau levels. And finally, just a few theoretical models for looking at high temperature superconductivity coming from lattices with flat bands, such as the Lie lattice. So what's interesting about flat bands is that your kinetic energy is suppressed, and so then you can have interactions or disordered dominated physics. And so this was motivation for us to look at, to create an analog simulator to look at flat band physics. Okay, so what platform are we interested in? In our lab, we do superconducting circuits. Specifically, we made qubits out of a transmon qubit, where we have a capacitor and a Josephson junction in parallel. The energy spectrum of this is a weakly anharmonic oscillator, where we define U to be the anharmonicity of the qubit, which is the difference in energy levels between the adjacent energies. Usually, the interaction strength is about 5% of the 0 to 1 transition energy. Okay, so we want to look at physics of particles on lattices. And in our platform, the qubits become our lattice, and microwave photons, which are these excitations on these qubits, become our particles. With this, we can couple a few qubits together. We'll do this capacitively, and this introduces a rate t at which these photons can hop between qubits. The Hamiltonian that we implement is given here, where the first term just counts the number of photons on each qubit. The second term takes into account the anharmonicity of the qubit and provides an effective interaction term between photons. And the third term allows these photons to hop back and forth at a rate t between the qubits. And this is exactly the Bose-Hubbard Hamiltonian describing bosons on lattice sets. Okay, so we're interested in flat band physics. So let's take a lattice that has a flat band. And one of the simplest lattices for us is this quasi-one-dimensional rhombus lattice, where here these circles are the qubits, and they're all coupled at a rate t to each other. If we look at the allowed energy levels of this, we see one band here that is flat, and then two dispersive bands. One of the reasons why we pick this lattice is because if we were to introduce a magnetic field in the system, such where you have a gauge field of pi, this means that if you start a particle on this side and you go around the loop, you pick up an analog bone phase of pi, so you come back on yourself with a negative sign. This is indicated by just putting one of these solid terms to be negative. Then all of your bands become flat. So what's special about a flat band? So flat band physics is described in momentum space. In real space, in the rhombus lattice, flat bands means that you have eigenstates that are localized in real space. So usually, if you have like a one-dimensional chain, all of your eigenstates are distributed across the whole lattice. But in this case, due to destructive interference, you can have an eigenstate that is a superposition of only two lattice sites. For completeness, this is what the compact localized states look like in the all flat band lattice. So what's special about this is that if all of your bands become flat, then every single eigenstate can be localized in space. And so any initial state that you put in, as long as it's localized, will be a superposition of just a handful of localized eigenstates, and will also remain localized in time. So this is the concept of aeronautical communication, where due to the interplay between magnetic field and lattice geometry, you have localized dynamics. So here's an example where I will put a particle on this side here and just let it evolve in time. And so we can see that it evolves to these 5 lattice sites, bounces around, but is spatially bounded beyond some boundary, and the absence of disorder and decoherence. If I were to put this particle on a different site over here, the boundary beyond which you get localization might be different, but you still get localized dynamics. So I'm an experimentalist. I have to make this in the lab. So luckily for me, I can look at this key physics by looking at just a single plaquette and observing whether initial states are localized to a subset of the plaquette. Okay, so now we'll move on to the experimental implementation of this. So this is the device that we made, where we have 4 qubits in this diamond shape. Qubits are transmon qubits that are given in green. We have individual flux lines for each qubit, so we can tune the qubits, change their frequencies, put them on and off resonance with each other. We then have individual readout resonators for each of the qubits, so we can read out the states of them. And finally, we have a transmission line where we can send pulses, excite the qubits and read out the states. Okay, what I really want to do though is I want to look at this localization physics with a magnetic field. Unfortunately for us, our excitations are photons, which are neutral, and so they will not respond to a magnetic field. So we have to play a geometric trick in order to implement a synthetic magnetic field. So we made 2 devices. First, zero flux device. This is just where you have all of your qubits in the same orientation. It turns out that if you want to implement a synthetic magnetic field of pi, in this geometry, all you need to do is rotate one of these transmons by 90 degrees. So this is how this works. If you think about these capacitors, these qubits, as being parallel plate capacitors, one of your plates will be positively charged, one will be negatively charged. And if you think about how we can tile these positive and negative plates, in the zero flux device, where we have all of the parallel plates in the same orientation, there's a really nice tiling we can do where all the positive plates are only coupled to negative plates. If we rotate this capacitor back, we see this frustration, where there's where here we have 2 positive plates having to touch each other. And so when that happens, you end up, if you go around the loop, you actually come back on yourself with a negative sign and this implements a synthetic magnetic field of pi. Okay, so now we'll move on to the actual experiments. So in these experiments, these are quantum walk experiments where what we do is we initialize the state, and then we let it evolve for some amount of time, and then we read out the qubits. We'll start off with the zero flux device. What we'll do is we'll put in a single excitation on the left qubit, and just let it evolve for some amount of time to the other qubits. The data is shown here. We're here plotting the population on each qubit, each of these 4 qubits, and on the bottom is a color bar just for visibility sake. So what we see here is that we start off with a particle on the left side, and it bounces around at some later time. It goes to the top and bottom qubits, and then it bounces to the right. It has this constant swapping between all these qubits. If we compare this to the pi flux device, we see something very different, where this is this flat band localization, where we start off on the left qubit, bounces up to the top and bottom, but we get decent interference to the right qubit. So this is indicated by the fact that the right qubit never gets any population. And one note, at late times, there's a small amount of population that appears, and this is due to slight disorder in the tunneling rates, and this is something that we can characterize really well. We ran simulations with individually measured qubit parameters, and we see incredibly close agreement between our experiment and simulation. All right, so that was all single particle physics. We're interested now in looking at the effects of interactions on the system. So what we'll do, we'll put 2 interacting particles on a single lattice site, and then, again, let it evolve in time. For superconducting circuits, that means going to the second excited state. Because we have strong interactions, these 2 particles become bound together, and they'll end up hopping as a pair. The way to think about this is that because of these strong interactions, these doubly excited states are energetically well separated from the state where you have 1 particle on each side. Because of that, you will end up having full coherent oscillations between these doubly excited states via a second order process through the 1-1 state. So you end up having full contrast swaps at a reduced tunneling rate of about an order of magnitude slower. And what's particularly special here is that because these 2 particles will hop together, each of them sees a phase of pi. Together, they see a phase of 2 pi, and so they should actually see effectively a phase of 0. Okay, so we'll start off with the dynamics two particles with a zero flux device. And here we see something very similar to the two particle and one particle dynamics, where we see full contrast oscillation between the left, right, and left and right qubits. Granted, the time evolution is much slower, given by about an order of magnitude slower. Next, we'll do this for the pi flux device. With the pi flux device, we actually see something very similar to the zero flux device, where now these two particles are interacting bound together, and they're able to delocalize across this plaquette in sharp contrast to the single particle physics. So this is this interaction-induced delocalization. Finally, we wanted to ask the question, do interactions always break localized dynamics? So we saw that just putting in interacting particles, these particles are now free to move. What happens though if we initialize two particles on opposite sides of the plaquette and make them collide and interact in the middle sites? Because the doubly excited states are energetically separated from states where we have two particles on different sites, we can look exclusively at the subset of 6 Fock states where we have particles on different sites. This is given in this diagram here, where each of these bars corresponds to connects the two lattice sites where we're going to have particles. So as an example, we start off in the site where we have a particle on the left and right. This is given by this black horizontal bar here. So in this, I will only plot the states top, bottom, and left, right, because this is where most of the difference in physics happens. Starting off with the zero flux device, we see full contrast swaps between the left and right and top, bottom states. Specifically, we start off in the left-right state. At some later time, we go to superposition of all 6 of these Fock states, and then we go to the top and bottom state. I will note, you see these coherent beating effects. This is due to the fact that we have finite interactions, and so we perturb the energy slightly and lead to coherent beatings. Finally, we do this for the pi flux device, and we see something very different, where now the dynamics to the top and bottom Fock state is prohibited. In this case, we start off with the left-right state, we go into superposition of all the states except the top bottom, and then we go right back to the left and right state. So this is similar to the single particle physics, where we had one lattice site that was unoccupied. In this case, now we have one Fock state where that's unoccupied. And this is interesting because this is even with strong interactions. So this is kind of different to the picture we had with putting two interacting particles on a single lattice site, delocalize everything. Here, even with strong interactions, we see some version of this localization. That provides some of the subtle and rich physics of flat bands and interactions, which we're excited to keep looking at. So to briefly summarize, we engineered a synthetic pi flux magnetic field and characterized the dynamics of an all-band flat plaquette. We first observed flat band localization for a single particle. Then by putting two particles on the same site, we observed this interaction-induced delocalization. And then by putting two particles on different sites with interactions, we observed some version of localized dynamics. This is a building block experiment. We just had 4 lattice sites, where we were able to see a lot of the rich physics. And now we can just extend this out to larger system sizes. The things we're excited to potentially look at is observing localization, delocalization conditions if we add in disorder in the system, or stuff like thermalization in flat bands. Briefly, acknowledgements. I want to thank my advisor, Andrew Howe, the postdoc of the project, Christy Chu, as well as Basil Smitham and Sarah Sussman. I encourage you to look at the paper. Thank you for your time, and I'm happy to take questions.
Thank you, Ernesto. Now, we have a question here.
Hi, thank you. I was wondering, would it be possible to tune your magnetic field such that you could reach something like the Hofstadter lattice model?
I guess would that require something? So in this geometry, we can only do 0 and pi flux. We can't do anything in the middle. However, if we do introduce, we can do stuff where we can introduce active elements. So if you introduce some interdecade coupling scheme, there you can introduce arbitrary magnetic fields. But in this case, we can only do 0 and pi flux.
Right. Any other question? If not, let's thank the speaker again.